The use of low-cost sensor in air quality monitoring networks is still a much debated topic. The engine presented here predicts jointly the concentration of particles whose diameter are below 2.5 and 10 micrometers, named PM2.5 and PM10 respectively. It is fed with the measurements provided by official air quality monitoring stations and low-cost sensors, as well as road traffic estimates. The two main conclusions of our study are the following. First, we highlight a strong link between the sensor density and the prediction accuracy. As an illustration, in areas with the highest sensor density, the low-cost sensor measurements bring a 25% and a 15% improvement in PM2.5 and PM10 mean square log error of predictions. Second, in some areas with high sensor density, the engine performs better when fed with low-cost sensors measurement only than when fed with official monitoring stations measurement only. This suggests that air quality monitoring networks composed of low-cost sensors is effective in monitoring air quality. This is a very important result because such a monitoring network is much cheaper to set up. The engine relies on two sources of air quality data. The United States official air quality monitoring network is formed with thousands of monitoring stations providing measurements on an hourly basis for the main pollutant harming people's health. As the low-cost sensor used in this paper provide measurement for PM2.5 and PM10 only, we focus on these two pollutants which are monitored by 974 and 328 official monitoring stations respectively. Official monitoring stations provide very accurate and reliable measurement of particulate matter concentrations. The low-cost sensors considered in this paper form a network of several thousand outdoor sensors providing PM2.5 and PM10 measurement every 10 minutes, along with other variables such as humidity and temperature. At any location L in the United States, we define the low-cost sensor density as the weighted sum of the number of sensors around. The weight being computed with an exponential kernel of length scales d equal to 10 kilometers. The figures show the location of official monitoring stations along with the low-cost sensor density in the United States. The engine approximates road traffic emissions through the use of road networks and traffic data. Road network data is collected as a set of road segments associated with the set of metadata. We have built two aggregate categories named roads and major roads. We define the feature roads D and major roads D for every location as a weighted length of roads and major roads around this location, the weights being computed with an exponential kernel of length scales d. We collect traffic data through a real-time jam factor over each road segment of a given area. The jam factor is a value between 0 and 10 measuring the road congestion. We define the feature traffic D at every location as the weighted sum of jam factors of the road segments around. The weights are computed with the exponential kernel. The training and evaluation datasets are built over the year 2019, which is 7 million data points and contain the PM2.5 and PM10 hourly monitoring station measurements the model is trained to predict, all the features used in the prediction model, including nearby station and low-cost sensors measurements, distance to the nearby stations and low-cost sensors, and road traffic estimates. Three prediction models are considered. Station model use station measurements and road traffic estimates. Sensor model use low-cost sensors measurements and road traffic estimates. And station and sensor model use all the features. The prediction engine maps the feature with the two-dimensional vector giving the concentration of PM2.5 and PM10 in microgram per cube meter. The engine is based on a classical neural network architecture with one hidden layer of N1 units. We use a more advanced architecture to process the low-cost sensors measurement. The last 16 PM2.5, PM10 temperature and humidity measurements are processed using a one-dimensional convolutional neural network. This network is formed with two sequences of convolution and max pooling layer. Kernel size and number of filters are denoted K1, F1, K2, and F2, and pooling size is set to 2. The output of the convolutional neural network is then concatenated with other features. It works much better in practice than providing the raw low-cost sensors measurement for the two following reasons. A naive choice would have been to average the last measurement provided in the last hour. However, the measurement can vary significantly within an hour, in particular when a pollution peak happens, and processing them with a convolutional neural network enables to keep much more information. Temperature and humidity are known to impact low-cost sensors measurement. Low-cost sensors classify particle size by mean of laser measurement. However, humidity can play a disturbing role during this measurement by increasing the size of particles that absorb water or by creating droplets through condensation. This phenomenon is difficult to model, so using them as a feature along with pollutant concentration measurements improve the prediction accuracy significantly. As the station model does not use local sensors measurement as an input, it is simply a fully connected neural network with a single hidden layer. To train this model, the set of official monitoring stations is split into two parts. 80% of the station form the training set, and the remaining 20% form the evaluation set. Given the key importance of the density of low-cost sensors in the analysis performed hereafter, the sampling of the official monitoring station is performed within each decile of low-cost sensor density. Hyperparameters of the models have been optimized and are shown in the slide. For PM2.5 and PM10, the datasets are split into 10 batches based on local sensor density. This figure shows the mean square log error computed for the three prediction models in each batch. The x-axis is the mean density on each batch. The main conclusion is that the improvement in accuracy of the station and sensor model compared to the station model increased with the low-cost sensor density. In the batch with the highest low-cost sensor density, the improvements are 25% and 15% for PM2.5 and PM10 respectively. The improvement brought by low-cost sensors is higher for PM2.5. This is due to the greater accuracy of low-cost sensors' PM2.5 measurements. Another interesting conclusion is that for PM2.5, sensor model is more accurate than station model as soon as the low-cost sensor density exceeds 1. We focus on the 5 cities with the highest number of low-cost sensors. This table compares the 3 prediction models in those cities. The table also gives the average low-cost sensor density at the official monitoring station, which are the locations where the models are trained. In all cities, the best performing model is the station and sensor model. The improvement compared to station model is generally higher for PM2.5 than for PM10. In cities where the mean sensor density is higher than 2, the improvement is very significant for PM2.5. 25% in Los Angeles, 13% in San Francisco, 23% in Sacramento, and 18% in Seattle. As an illustration, this figure shows the map of PM2.5 rate in San Francisco predicted at a given hour. The left map is built with the station model, while the right map is built with the station and sensor model. We see that the right map shows much more spatial variability, for example, around Richmond and San Jose. This time, the figure shows the map of PM10 rates in Los Angeles. Once again, the model using the sensor network data shows greater spatial variabilities in air quality and appear to better capture local pollution peaks. This work is, as far as we know, the first paper assessing the use of low-cost sensors measurements at such a large scale, which make the two conclusions given at the beginning robust. First, low-cost sensor can be used to improve the prediction accuracy. Second, an air quality network composed of low-cost sensors only can be effective in monitoring air quality. We see three main improvements: to use low-cost sensors measurement or part of them as ground truth measurements. This choice leads to larger but noisier dataset. Given the high impact of low-cost sensors measurement processing on the engine performance, this part of the engine could be improved further to make the most of low-cost sensors data. Finally, this paper focuses on air quality spatial variability. A logical improvement would be to study how low-cost sensors can help to model air quality temporal variability.